Welcome to the REWIRE Risk Assessment Platform demonstration video. In this demonstration, we highlight the main characteristics of the risk assessment engine. We describe how this engine fits into the entire REWIRE architecture, and we describe some main internal subcomponents of the risk assessment engine. All this information will set the scene for our demonstration part, where we describe a specific example stemming from one of the REWIRE use cases, namely the Smart Automotive domain. First of all, maintaining a continuous risk assessment process is crucial in order to have an up-to-date overview of the risk posture of each device in the topology. Starting from the design phase and along with other processes such as the formal verification and the software firmware vulnerability analysis process, it is essential to get an up-to-date view of the risk score of each device. At the same time, moving to the operational phase, it is essential to extract runtime risk indicators so as to update these risk scores. Some key characteristics of the REWIRE risk assessment platform are now presented in the slides. First of all, it is essential that the REWIRE risk assessment platform supports various methodologies in order to cover as many domains and threat vectors as possible. To that extent, in this demonstration, we are going to discuss about the CVSS-based methodology that is currently supported in the context of the first release. But at the same time, we will showcase the need for supporting an attack path assessment in order to calculate and identify the cascading attacks in the edge topology, but also we are going to discuss about the need of having domain-specific risk assessment methodologies, such as the TARA methodology that is focusing on the automotive domain. This need for supporting multiple risk assessment methodologies creates the challenge for automating the respective threat analysis that needs to be carried out by security administrators. And this involves not only the identification and management of threat scenarios, but also their impact in the risk assessment process and how various security controls affect these risk results. At the same time, when it comes to the runtime phase, it is essential that the risk assessment engine reacts and responds to various risk indicators in order to better depict the risk posture of the devices. Finally, in the context of REWIRE, the risk assessment platform constitutes a core enabler for assessing the trustworthiness of the devices, but also of the data flowing the edge topology. Hence, regardless of the risk assessment methodology employed, there needs to be a harmonization layer in order to pass the risk results in a common scale as much as possible. But at the same time, this information needs to be carried out in a later stage to an overall trust assessment framework, hence the need for transparency. Now, when it comes to the preparation of the trustworthiness, we are mainly focusing on two specific pillars. First of all, through the risk assessment results, it should be possible to identify the required trust level, or RTL in short, which defines a specific threshold that the devices need to attain in order to be considered trustworthy. At the same time, the risk assessment results help identify the trust policies that need to be enforced during runtime in each of the devices. This also includes the various trustworthiness evidence that need to be collected during runtime in order to evaluate the actual trust level of each device or data item. Such trustworthiness evidence include also attestation evidence, as we will see below. So moving on to the REWIRE architecture, we can see in the top right-hand side of this diagram that the risk assessment is connected both with the design phase and the security administrator configuration process, but also with the runtime phase and specifically with the REWIRE-enabled edge devices. But first things first, we can see that during the design phase, the security administrator needs to perform its threat analysis. And by that, we are referring to specifying the asset topology of how all the edge devices are interconnected, along with various operational and security policies and other requirements. This process includes also the identification of possible threats and vulnerabilities associated with each of these devices. And all this information will enable the risk assessment platform to perform its analysis and calculate the overall risk graph for the topology. This information is given to the security administrator to proceed with the design phase procedures, including the identification and specification of the overarching requirements needed for the software and hardware co-design formal verification process. And eventually, this will enable the security administrator to specify the soft requirements to be enforced by the orchestrator in the edge devices. Once these requirements have been defined, they will be also processed by the software firmware validation component in order to ensure vulnerability-free binaries that are going to be deployed in the edge devices. During runtime and throughout the operational lifecycle of the edge devices, various evidence and risk indicators are collected. This involves not only attestation evidence, but also anomaly detection reports. And all this information is also shared with the risk assessment platform in order to carry out its analysis and update the overall risk graph for the topology. Now that we have positioned the risk assessment platform within the REWIRE architecture, let's delve into a bit more into the internal subcomponents of the platform. First of all, we can see in the middle of this diagram the holistic backend, which basically orchestrates all the interconnections between the various subcomponents of the risk assessment platform. Apart from this main component, we also have the asset modeling and visualization subcomponent, which is already implemented in this first release, as well as the vulnerability and threat modeling component in order to model the overall threat scenarios of each asset. At the same time, we also have the attack path calculator component that is responsible for identifying the cascading attacks that an adversary could leverage in the entire topology, and also the mitigation strategy management component that is responsible for performing comparisons between different risk assessment processes in order to evaluate the effectiveness of various controls employed in the topology. Last but not least, there is the risk quantification engine that is basically responsible for supporting various risk assessment methodologies. A threat analysis is assumed to be carried out by the security administrators beforehand, and this implies a set of input to be given to the risk assessment platform. This input refers not only to vulnerabilities and threats coming from either external sources or from the security administrator itself, but also the asset topology coming from the operational environment, meaning the edge devices deployed and the security requirements as well. For the purposes of this demonstration, we want to describe an example coming from the second use case related to the smart automotive domain. First of all, in the context of the risk assessment platform, we want to model the in-vehicle topology, and this implies describing all the assets and interconnections from within the in-vehicle computer and the surrounding zonal controllers and peripheral sensors and ECUs. Now, this is the result, as we will see in the demonstration. So, let's go to the demo. What we see here is the risk assessment platform graphical user interface, where security administrators can log in and perform their risk analysis. By logging in with one of the available credentials, we can see the main dashboard, where we get a quick overview of the number of assets inserted in the engine, the number of topologies that we have inserted, and the number of risk assessments, for instance. In additional information, we can also see the number of vulnerabilities stored in the knowledge base of the risk assessment engine, or the number of threats or security measures that we have inserted. So the first thing that we want to do is to visualize the topology that the security administrator has inserted. So by looking here, we can see all the various assets comprising the topology, starting from the ADAS NVIDIA drive, for instance, where we have a hypervisor and a guest operating system, on top of which the ADAS logic software binary is installed. And this binary has as a dependency the third-party NVIDIA SDK. Now, through an Ethernet switch, there is the connection with the zonal controller 1 and 2 that are both interconnected with this relationship. And we have the zonal controller 1, on top of which we have a connection with the powertrain ECU, where the software binary is running. Now, both zonal controllers are connected with a set of peripherals and sensors from the in-vehicle topology, such as the speed sensor, the torque sensor, or the electronic power steering. Now, for each capable ECU, we also have a real-time operating system installed on top of it. Now, this is one part of the threat analysis that the security administrator needs to include in order to run the CVSS-based risk assessment methodology. Now, the second information is related to the vulnerabilities and threats. By looking at the Open Intelligence tab, we can see a list of various CVEs along with their impact. And the impact is measured through the CVSS specification that identifies a specific score from 0 to 10. By looking into more details, we can see all the different attributes that contribute to this base score vulnerability impact, such as the access vector, the access complexity of this vulnerability, and so on and so forth. And of course, this CVSS specification defines various versions. At the same time, we have also the definition of various threats. And by threats, we are referring to the CAPEC specification, where various types of threats and attacks are defined. Now, with all this information, it is possible to define in order to calculate the risk graph of our topology. Now that we have initiated this risk assessment task, we click on the execute button and we can see the executive summary here. What we can see here is that there is an aggregated risk report that showcases how many assets are classified with a risk of high and how many of them with a risk of medium. For the CVSS-based risk assessment methodology, for each of the attack scenarios, the result is based on the vulnerability impact and the threat probability, a value that signals the likelihood of a specific threat to take place in our topology. Now, we can see in this heat map that 36 vulnerabilities are identified with a threat probability of high, but a vulnerability impact of medium. By clicking on this button, we can see that most of these scenarios refer to the real-time operating system in the powertrain ECU. Now, as an additional report, we can also get the visualization, but this time we can see the different colors representing the different risk values for each asset. Now, for example, we can see that the powertrain software binary is assigned with a risk value of medium, while the associated operating system with a risk level of high. A crucial note that can be made here is that this CVSS-based methodology focuses on identifying the individual risk level for each asset separately. However, it is essential to identify the possible cascading attacks that could take place in our topology in order to better prioritize which vulnerabilities need to be addressed as a first and high priority. To that extent, we plan to fully support the attack path assessment methodology in order to identify all these possible attack paths, starting from a specific asset and spanning across one or more neighboring assets within the topology. For instance, in this case, we can see that there is one vulnerability, so one entry point to this powertrain software binary, but there are 14 different vulnerabilities, so 14 different attack paths that could lead to a cascading attack starting from this binary to the operating system. And of course, this could even span to more assets across the topology. Now, assuming that the OEM and the security administrator have already performed their initial threat analysis according to the TARA methodology, it is possible to run an initial risk assessment task in order to capture and depict the overall risk graph of our topology. Then we initiate the task, and before executing it, we can actually configure it. First of all, what we can see is that we haven't taken into consideration any controls. And one of the core elements of the TARA methodology is the identification of the generic damage scenarios that could take place in our topology, and in our case, in a car. For each damage scenario that the security administrator has identified, we can specify the overall impact of this damage scenario to the environment or to the SECAM service, for example. In addition to that, the second key element of the TARA methodology is the identification of the attack paths, so the cascading effects that may involve more than one asset, and an adversary could exploit and pivot from one asset to another in order to launch a complex and cascading attack. Now, in this table, we can see all the different attack paths and the number of assets involved in this chain of attacks. And we can see the target asset that is impacted based on this attack, and the target property that is compromised. So with that in mind, we are ready to execute our first TARA risk assessment process. By clicking on the play button, we can see that the process has been completed successfully. Now we can inspect the risk results. First of all, what we get to see is the damage scenario to attack feasibility heat map, characterizing all the risk scenarios that have been derived through the TARA process. This is a good overview to help us prioritize the risk scenarios depending on their importance and criticality with respect to both attack feasibility rating and damage scenario impact. In addition to that, the report shows also a detailed description of all the risk scenarios and associated damage scenarios, and the calculated risk value, where we can see that we have two risk scenarios identified as very high, and most of the rest of them are marked with a risk value of high. Parallel to this risk assessment analysis performed for use case 2, we have conducted a similar approach for the remaining REWIRE use cases. Concerning the first use case, smart cities, we have instantiated an asset topology where a specific web server is connected through a gateway board to the end devices where various traffic light sensors and pedestrian triggered switches are connected in a specific end device on top of which a set of applications is running. When it comes to the final use case, this is the topology that we have instantiated so far, where we have a single mission control center connected to two reference ground stations, which are able to communicate with a specific satellite in orbit. To conclude this demonstration, first of all, the goal is to finalize the instantiation of the use cases in this risk assessment platform and evaluate the relevant KPIs to be reported in deliverable 6.1. As a final short-term goal, it is envisioned that the risk assessment platform supports the realization of the required trust level, which is essential for making any trust-related decision in the context of an overarching trust assessment framework. Moving to the long-term goals, these are mainly related to integration action points. On the one hand, we have the integration points with respect to additional risk assessment methodologies, such as the finalization of the attack path assessment or domain-specific risk assessment methodologies such as TARA. On the other hand, the risk assessment platform needs to be integrated with risk indicators retrieved during runtime, such as attestation evidence or even misbehavior detection reports. At the same time, the risk graph needs to be integrated with the software vulnerability analysis tool in order to evaluate additional fuzzing tests to be enforced during the testing of software vulnerability analysis process. On a similar note, we will work on the finalization of the RTL implementation, but also work on how the risk results could be associated with the identification of the trustworthiness evidence, such as attestation mechanisms that need to be collected for each device. Thank you for your time. Now, assuming that the OEM and the security administrator have already performed their initial threat analysis according to the TARA methodology, it is possible to run an initial risk assessment task in order to capture and depict the overall risk graph of our topology. Then we initiate the task, and before executing it, we can actually configure it. First of all, what we can see is that we haven't taken into consideration any controls. And one of the core elements of the TARA methodology is the identification of the generic damage scenarios that could take place in our topology and in our case in a car. For each damage scenario that the security administrator has identified, we can specify the overall impact of this damage scenario to the environment or to the SECAM service, for example. In addition to that, the second key element of the TARA methodology is the identification of the attack paths, so the cascading effects that may involve more than one asset, and an adversary could exploit and pivot from one asset to another in order to launch a complex and cascading attack. Now, in this table, we can see all the different attack paths and the number of assets involved in this chain of attacks. And we can see the target asset that is impacted based on this attack and the target property that is compromised. So with that in mind, we are ready to execute our first TARA risk assessment process. By clicking on the play button, we can see that the process has been completed successfully. Now we can inspect the risk results. First of all, what we get to see is the damage scenario to attack feasibility heat map, characterizing all the risk scenarios that have been derived through the TARA process. This is a good overview to help us prioritize the risk scenarios depending on their importance and criticality with respect to both attack feasibility rating and damage scenario impact. In addition to that, the report shows also a detailed description of all the risk scenarios and associated damage scenarios and the calculated risk value, where we can see that we have two risk scenarios identified as very high, and most of the rest of them are marked with a risk value of high.